10-1, Exploring Conic Sections. The objective of this section, to graph and identify conic sections. Lesson vocabulary, conic section, and an essential understanding. There are 4 types of curves known as conic sections: parabolas, circles, ellipses, and hyperbolas. Each curve has its own distinct shape and properties. Consider this. A plastic foam cup has the shape of a cone with the point removed. Suppose you make a planar cut through a coffee cup. So that means a straight slice. Imagine, if you will, a ninja slicing the cup. Then you press the cut edge in ink and stamp the edge on a piece of paper. What would be the shape of the print? What different shapes could you print by slicing whole cups at different angles? Explain. In Chapter 4, you studied parabolas. Geometrically, a parabola has the shape of a cross-section of a cone that you cut in a particular way. Parabolas form a family of curves that belong to a larger family known as conic sections. For your notes, a key concept: conic sections. A conic section is a curve you get by intersecting a plane and a double cone. By changing the inclination of the plane, you can get a circle, a parabola, an ellipse, or a hyperbola. You can use lines of symmetry to graph a conic section. Example problem 1, graphing a circle. What is the graph of x squared plus y squared equals 25? What are its lines of symmetry? What are the domain and range? So let's back up. What is the graph of x squared plus y squared equals 25? If you were asked to provide a graph like this, what would you do? I bet you would grab for your graphing calculator or go to Desmos. But in what world will everyone carry around a graphing calculator in their pocket? So what if you had no access to the internet or to a graphing calculator? Well, you'd probably fall back on the tried and true technique of making a table of values. So we've been using tables of values since, well, way back. And they've been helping us to graph equations, particularly before we know tips, techniques, maybe even tricks to graph things more easily. So we check out this equation: x squared plus y squared equals 25, and maybe we want to try one of those really easy values of x to substitute in. So we start with 0. It's often nice. Math with 0 is usually user-friendly. So we substitute 0 for x into our equation. 0 squared is 0, plus, well, now we have y squared must equal 25. Well, we know there are 2 square roots of 25, both positive and negative 5. So this will have something somewhat interesting take place when we go to graph these points. We really have 2 points represented here. Right away, this indicates to us that this equation does not represent a function. All right, most often, after using 0 for one input value, we would move on to 1, because 1, again, is a pretty user-friendly number when doing calculations. Multiplying by 1 is sure easy. Adding 1 isn't much more difficult. So then we substitute 1 in for x in the equation, and we get 1 squared, well, that's 1, plus y squared equals 25. Now we realize perhaps if this equation were rewritten or solved for y, that would make our job a little bit easier. So maybe we set to work to do that. Alright, so that's nice. Now we substitute 1 in for x, we get 25 minus 1, the square root of 24. And that's not a really friendly number for us. It'd be nice if we could use integers. So maybe we should backtrack. Let's consider what other values of x might we use that work out nicely given this equation. So, well, 25 minus, we're thinking of perfect squares. 25 is a perfect square. The next lower perfect square 16. So if we could make 25 minus x squared equals 16, we'd be in business. Well, the x value it would take to do that, we'd have to subtract 9, so x would have to equal 3. So if we let x equal 3, we're doing ourselves a favor. We get to work with integers, which are going to be really useful all along the way. Lower than 16, our next perfect square is 9. What do we have to subtract from 25 to get 9? Well, we'd have to subtract 16. So let's plot these points. Bear in mind, I'll do a quick sketch so you get the idea. For more detail, we can actually look at the example down here to the left. That looks really nice. Anyhow, our points, 0 and positive 5. Let's say there is 5 on the y-axis. And also 0 and negative 5, so it's reflected image. Down here we have two y-intercepts, 3 and positive 4 and negative 4. So if we go out 1, 2, 3 units and up 4 units. And also down 4 units. And then we do, well, 4 and plus or minus 3. 1, 2, 3, 4. And plus or minus 3. Beginning to think I really, well, it's just not looking quite circular. I think we get the idea though. What we have going on here, if I can sketch it, I'm really trying to go with the Sal Khan style sketches. Well, here we have what looks to be a semicircle. Now, what if we had plugged in some negative values? So a negative 3. Well, notice in our equation we were squaring that immediately. Right? The negative values would be squared, and they would then turn into the same thing as their positive counterparts. So negative 3, when substituted in for x, would also give us a plus or minus 4. So what we end up with, as you probably noticed, is a mirror image of all of these points on the left-hand side of the y-axis. That's one of these axes of symmetry that was discussed over here. I'm sorry, lines of symmetry in this context. The line of symmetry of the y-axis means that whatever we see on the right of the y-axis, we can consider its mirror image on the left of the y-axis. Now, in a circle, and as we've seen so far here, the x-axis is also a line of symmetry. Therefore, every point down below the x-axis will have a mirror image point above the x-axis. And we end up with a circle. So let's suppose for a moment that you do live in that crazy world where everybody walks around with a graphing calculator in their pocket, and you would like to graph this using some form of graphing utility. Well, this would be the form you'd most likely want to plug in to that graphing utility in order to get the graph. Most graphing utilities, I think I can say that confidently, most wouldn't deal very well with an equation written this way. You'd need to solve it for y or your output variable. Another thing to keep in mind is that graphing utilities graph functions. And notice this is not a function, right? It doesn't pass the vertical line test. A vertical line constructed in many locations would intersect this equation or this graph in multiple places. So let's see what happens when we do graph this equation on Desmos. We only get the top half of the circle, and you'd see very similar behavior on your graphing calculator. We recognize that there should also be the other half of the circle, or the reflected image of this across the x-axis. But graphing utilities won't graph that for you, so it is up to you to graph the negative version of the same function. And there we have a complete circle. All right, so let's finish up this problem. What is the graph of x squared plus y squared equals 25? We've got that. What are its lines of symmetry? Well, we've discussed the lines of symmetry. The two primary ones we used are the x and y axis, but consider, are there more lines of symmetry? Consider any line through the origin. And finally, what are the domain and range? Recall, domain represent all of the x values or the input values of the function. Our function extends from -5 to +5 in terms of its x values, so -5. And our range refers to our y values, and it's something very similar. -5 in terms of y, well, -5 is less than or equal to our lowest y value, so y is less than or equal to 5. So these compound inequalities provide for us all of the x and y values that our graph assumes. And the opportunity you've been waiting for, a chance to show that you have got it. A, what is the graph of x squared plus y squared equals 9? What are its lines of symmetry? What are the domain and range? Sounds strangely familiar. And B, a reasoning problem. In problem 1, why is there no point on the graph of x squared plus y squared equals 25 with an x coordinate of 6?